Hello mga ka-Gigi! Andito na naman tayo ngayon sa J Channel. May kasabihan tayo, ang hindi sumubok, walang resulta. Tara, subukan natin. Ang tatalakayin natin ngayon ay ukol sa mathematical induction. Mathematical induction. Sometimes we want to prove that a statement about positive integers is true for positive integers. Perhaps for some finite or infinite sequence of consecutive integers. Such proofs are accomplished using mathematical induction. The validity of the methods rests on this axiom of the positive integers. Let S be a subset of positive integers satisfying one element of S, and if K is element of S, then K plus one element of S. Then S is equal to the positive integer. This axiom leads immediately to the method of mathematical induction. So let P of n be a statement concerning the positive integer n. Suppose that P of 1 is true, and if P of k is true, then P of k plus 1 is true. Then P of k is true for all n element of positive integer. So bear this in mind that P of 1 must be true, then let P of k be true, then P of k plus 1 must be true. Most of the time, we want to show that P of n holds for all n element of positive integers. So if we wish only to show that it holds for r plus 1, r plus 2, and so on, s minus 1, and s, then we show that P of r is true and that P of k implies that P of k plus 1 for k is greater than or equal to r but less than or equal to s minus 1. Note that r may be any integer, positive, negative, or 0. Example number 1, prove the formula. The formula that we had is 1 plus 2 plus and so on plus n is equal to n times n plus 1 all over 2. So here's the formula that we have. So we will show using the mathematical induction. So we let P of n be the statement that formula 1 is true for n is equal to 1. So if n is equal to 1, then we obtain, replacing n equal to 1, so that would be 1 times 1 plus 1 all over 2, 1 times 2 all over 2, so 2 divide 2, that is 1. So P of 1 is true. Suppose k is greater than or equal to 1 and P of k is true, our induction hypothesis, so we have it here. K is equal to k times k plus 1 all over 2. For the third step, to show that P of k plus 1 is true, we compute, so put k plus 1. From the second step that we had, we add plus k plus 1 to both sides. Then, from these equations here, we simplify, and the resulting simplification we have is k squared plus k plus 2k plus 2 all over 2. Then k plus 2k can be added together because they have the same variable k. So it becomes now 3k. K squared plus 3k plus 2 all over 2. And we factored out k squared plus 3k plus 2. That would be k plus 1 times k plus 2 all over 2. Thus, P of k plus 1 holds and formula 1 is true for all n element of positive integers. Second example. Show that a set of n elements has exactly 2 raised to n subsets for any non-negative integer n. We start the induction process with n equals 0. Let S be a finite set having n elements. We wish to show that S has 2 raised to n subsets. So P of n must have 2 raised to n subsets. If n is equal to 0, then S is the empty set and has only one subset, namely the empty set itself. Since 2 raised to 0 is equal to 1, we see that P of 0 is true. Suppose P of k is true, then let S have k plus 1 elements and let one element of S be C. Let S minus C is equal to x element of S such that x is not equal to C. Then S minus C has k elements and hence 2 raised to k subsets. Now every subset of S either contains C, does not contain C. Those not containing C are subsets of S minus C. So there are 2 raised to k of them by the induction hypothesis. Each subset containing C consists of one of the 2 raised to k subsets not containing C, with C adjoined. Adjoined, which means not joined. There are 2 raised to k such subsets also. The total number of subsets of S is then 2 raised to k plus 2 raised to k, 2. 2 of 2 raised to k. So as you can see here, applying the law of exponent, we have imaginary 1 here. So applying the law of exponent, it becomes now k plus 1 with the base 2. So as you can see, P of k plus 1 is true. Thus, P of n is true for all non-negative integers n. For our third example, let x element of real number with x greater than negative 1 and x not equal to 0 show that 1 plus x raised to n is greater than 1 plus n times x for every positive integer n is greater than or equal to 2. We let P of n be the statement. So 1 plus x raised to n is greater than 1 plus n times x. Note that P of 1 is false because we have it here that every positive integer n is greater than or equal to 2. So let b n equal to 2. So P of 2 is a statement. 1 plus x raised to 2 greater than 1 plus 2x. So here's the statement. Note that 1 plus x raised to 2 is equal to 1 plus 2x plus x squared. So simplifying that, we have here, if we expand, so x squared is greater than 0 since x is not equal to 0. Thus, 1 plus x squared is greater than 1 plus 2x. So P of 2 is true. Suppose that P of k is true. So by letting n is equal to k, then we have now 1 plus x greater than 0 since x is greater than negative 1, multiplying both sides. 1 plus x raised to k greater than 1 plus kx by 1 plus x. We obtain, by multiplying both sides by 1 plus x, so we obtain 1 plus x times k plus 1 plus kx squared. Since kx squared is greater than or equal to 0, we see that P of k plus 1 is true. Thus, P of n is true for every positive integer n greater than or equal to 2. So in a frequently used form of induction known as complete induction, the statement if P of k is true, then P of k plus 1 is true. Here are some exercises. Prove the following using mathematical induction. Here is the solution of problem number 1. As you can see, it shows the steps in mathematical induction. Here is the solution in problem number 2. So same steps in mathematical induction. Here is the third problem and its solution, showing the mathematical induction. Fourth problem, showing the mathematical induction process and for the continuation of the steps, and it shows that it is true for n element of positive integers. For problem number 5, prove by induction. So here's the process. Step 1, P of 1 is true. For step 2, suppose that P of k is true. And for step 3, P of k plus 1 is true. For the conclusion, it is true for n element of positive integers. Hope you learn. Try and try until you can do the best. Positive lang ta always. Nothing is impossible if you just try.